Okay, so we can solve the small problem, but now we're trying to see whether we can gain some knowledge, some insight that would help us solve bigger problems. The observation is that when we change the coefficients of the objective function, x1, the 1, and the 2, for the same feasible region, for the same constraints, and when we change the objective, that will change the slope of this line here. Right, this slope, this line here, it will change slopes. But no matter what its slope is, if it starts slanting this way, it will hit upon this corner point. If the numbers really go haywire and go negative, it might even go this point. And if the numbers change a different way, it might hit this point. And never will there be a point in the interior part of this area that will be better than the ones at these corner points. Now, there might be some that are equally good. There might be some on this line that are equally good to either of those corner points. But the corner points are always the optimal solutions. The optimal solutions are always at the corner points. So that is the basic insight that we can state. So we want to make something out of this. We want to say, okay, well, so what? Well, the way we get the so what is by putting this problem in something called a standard form. So one of the reasons for putting the problem in standard form is that mathematically, algebraically, we have a little bit of difficult dealing with inequalities. We would much prefer dealing with equations. So we're going to in standard form, the LP becomes maximize x1 plus 2x2 subject to x1 plus 3x2, and now we're going to introduce what's called a slack variable. So this measures the extent to which we're not at 16. So if x3 is 0, then we're right at and we're tight. But if x3 is 5, that means we have some slack. And if x3 is negative, then we're not, then we're violating the constraint. So this will be x1 plus x2 plus x4 equal to 7, and then we'll have x1, x2, x3, x4. All of these have to be greater or equal to 0. So let's see what is a corner point algebraically. Well, we know that we have two equations, and equations typically solve if you have the same number of variables, like two equations and two unknowns, you can easily solve. If you have 320 equations, then 320 variables you can solve. So we can, in general, what we will have, so can always solve a system of n equations in n unknowns. And this is assuming that there's some conditions. Okay, some conditions have to apply, but usually if a system is well behaved, we can have. So you can always do that. So in our case, can set any two variables to 0 and solve 2 by 2 system. And when we solve that 2 by 2 system, we will obtain a basic solution. So a basic solution is any solution where if you have more variables than unknowns, like in our case, we have 4 variables, 2 constraints, and 4 variables, 4 unknowns and 2 constraints, then make it equal, set 2 of the 4 unknowns to 0, and then solve it 2 by 2. And if we do that, we get a basic solution. Suppose in an LP with n variables and m constraints, you can set, so we have m constraints, so therefore that results in standard form, we will have n plus m variables and m constraints, and then can solve, set n variables equals 0, and then solve the m by m system. That will give you then a basic solution. Now, we're not just interested in basic solutions, we're interested in solutions which are also feasible. Make the statement right here that if the basic solution has all variables greater or equal to 0, then it is a basic feasible solution. Now, this will become a little bit clearer when we do the example.